Okay, now I can share. So let me see if I have to share the screen number 1 or screen number 2. I think it's screen number 2. So while my presentation is full screen, I'm not able to see what's happening within the Zoom settings. So please don't hesitate to interrupt me at any time if something is not working fine. Okay, so I think now we can get started. So in 1 or 2 seconds, now you should be able to see my presentation as full screen. Is it correct?
Yes.
Okay. So first, thank you for your invitation to present my research interest here. So it's never had the opportunity to travel to Pakistan, but it's a good privilege to be able to be with you for this presentation virtually. So the title I have given to my talk is Exploring the Center of Active Galaxies. So what I will do is try to invite you to virtually go to see what is lying at the center of some galaxy that we call active galaxies. And we will see why we call them active galaxies and what's the difference with a normal galaxy. And I will try to first spend time to introduce the historical background, how throughout the second half of the 20th century, we went to the discovery and the understanding of this quite, would say, exotic objects. So here you can see my name. So Saida has already introduced me. And I want just to also give credit to my main collaborators working with me, many people from South Africa, but also from France and Russia also, people with whom I have written the previous 2-3 papers, but the list is not exhaustive because since I'm doing experimental work, then it always involves a lot of collaborators working at different wavelengths with and also with theorists. So I will just start with a quiet night sky in what we call the Cévennes, which are hills in South France, not far from my home. And this is a picture I took already several years ago. So it's visible light. So this is the night sky, the way we can see it by night. We don't see many changes from one day to another day, even though some stars are variable. But when we consider gamma rays, then it's a different picture. Then here you can see, sorry, I can hear some background. Maybe someone has a mic which is not muted. Is there any question? Okay. So this is, sorry, what I want to show is that the universe is very agitated in terms of gamma rays. So it means from one night to another night, or sometimes even within a few hours or even a few minutes, we can see some flash of light and then it disappears. Then it can be a gamma ray burst, as you can see illustrated here. I guess you can see also a mouse when I move it here. And here you see a blazar. So we will talk later on what a blazar is. So these maps here are in galactic coordinate. It means what is bright at the center is the light emitted by the galactic plane where a lot of gas clouds are lying. So of course there are false color here. It's an intensity map. And on the left here, you can see all the different gamma ray bursts which were detected by the Swift satellite at hard X-ray soft gamma ray. So this is to show that at high energy, the sky is very much variable. Sorry, can everyone mute the mic, please, because I can hear still some noise behind. So now I would like to bring you to a journey to go where no man has gone before, as we can read in Star Trek. And this is the outline of my talk. So I will start with an historical introduction on active galactic nuclei. Then I will talk about the AGN unified model. Okay, can you hear me well? Because there is very strong background. I think someone has a mic which is not muted. I think it is from Tayaba. I don't know, maybe the host also can mute most people. Okay, thank you very much. So I will try to go back to this coming slide. Yeah, so historical introduction. Then I will talk about what we call the AGN unified model. So AGN stands for active galactic nuclei, this nuclei of a galaxy which is active. Then I will present some telescopes, mainly the Fermi Gamma Ray Space Telescope on which I'm working, and also some ground-based optical telescope. I will address a few current challenges and give a few results, and then conclude by giving some perspective and also for students who will be interested to work in this field, what are the different possibilities to access data freely and to be part of a coming exciting project. So the historical introductions, then it would be nice to start with from the 17th century, but I'm not sure at what time you want to go for dinner. So I think I won't have time to talk about everything. But it's always good to remind us about what spectroscopy is and the fact that it is thanks to this type of experiment that we are able now to do astrophysics. In fact, before spectroscopy, we were able to do only observations, astronomy, but the physics applied to astronomy are started with the use of a spectrograph to study the light coming from the stars. So here we can see Newton with this famous prism experiment in 1666, when he was able to observe that the white light from the sun, in fact, is made of radiations, different colors. But then not only that, but then atomic lines were observed from the beginning of the 19th century by Joseph van Fraunhofer. So what he has seen is that he has seen absorption lines. So not only the continuous light that you can see here, but at some places, some specific wavelengths, he saw absorptions, and it was the signature, it has been well calibrated in laboratory. It was a signature of some specific chemical elements. So I guess you are all familiar with that. But I would also like to talk about the Doppler effect, which has a very big importance in astrophysics when we observe stars, because it allows us to know if a star or a galaxy or whatever object we observe is moving towards us or away from us. In fact, it's a relative motion. It can be us moving away or towards this source. And if we can measure the redshift, the shift in wavelengths, then we are able to know what is the velocity, relative velocity between the source and the Earth. And it also allows us to know at what age of the universe it corresponds, because of the time that the light travels towards us. Not only this, but now we are able to do astronomy using all wavelengths of the electromagnetic spectrum. You can see that, of course, we are all familiar with optical telescope. on the ground or in space, like the Hubble Space Telescope, but we can also do observation in the infrared, in the radio, in the ultraviolet band, and also in X-ray and gamma rays. But we mainly we use always very different techniques. I won't go into detail. And now we start our history. So radio astronomy, which is a very important branch of astrophysics now, it has started, in fact, with a first detection from the center of the Milky Way, radio wave, in 1933. So I think we were too young, all of us, to remember this, but it was very interesting to be able to detect radio waves from the universe and not only optical band. And then in 1939, Groth Reber, not sure pronunciation of his name, but he discovered the first radio galaxy, which is called Cygnus A. It's the most powerful extragalactic radio source in the sky. From all the sources beyond our galaxy, then it is the strongest. And this is the graphics and the image at that time. But now let's go back to the future, the way we are able to look at Cygnus A now. So you can see here an optical image with a Hubble Space Telescope with a dimension of only 5 arcseconds, which is quite small. And but at that time, our optical telescopes 100 years ago were able to see only a small point. But you can see that at very large distance, you see the scale. Here it's only 5 arcseconds, it's 10 arcseconds. You can see jets and what we call radio lobes. And that's something that we could see only very recently. But at that time, the only thing we knew is that we have a galaxy which looks like an ordinary galaxy, but it emits a lot of radio wave. That was very surprising. We had no explanation at that time for that. But today, try to remember later what you can see on this picture. Like in optical, you don't see much. This is the optical, this is a radio, but you see very large radio waves extended to large distance. Now let's go back to the past again, 1943. Carl Seifert, an American astronomer, has discovered 6 galaxies with something very peculiar, that the center of this galaxy were very bright. For comparison here, a picture of a normal galaxy where you can see the center is bright, but not so bright compared to the rest of the galaxy. Here again, these are not the original observation by Carl Seifert. They were made later with a Hubble Space Telescope, but they are the same sources that Carl Seifert observed, and he noticed very, very peculiar aspect. We cannot explain such luminosity by only putting stars at the center of the galaxies. We won't have space to put all these stars. The stars are not so bright to be brighter as the whole galaxy like we see here. It was published, but it was still, people didn't pay so much attention at that time. Then during the 40s, 50s, we got more detailed radio maps. A lot of new sources were observed, but not only radio galaxy, but also radio sources for which no clear optical counterpart were identified. So these sources were called quasars, which is an acronym for quasi-stellar radio sources. And we were not able to really know what these sources were until the early 60s. So the 48 sources of the third Cambridge catalog, called 3C48, then was the first to be associated, and this radio source to be associated with what looked like a very, very faint blue star here at the center, here on this image. So you don't see much. I think it was 16th magnitude in optical magnitude. So it was a work carried by Alan Sandage and Thomas Matthews. And through radio interferometry, he was able to have some relative precise measurement, and it was found at about 4 arc seconds of a position. So the radio source was close to this optical object. And this is a spectrum they obtained at that time. So you can see the identification of the lines, but at that time we could not understand anything. This spectrum looked very, very strange. Then what an important also discovery was made with 3C273, which is the brightest optical, what we call Quasar or Blazer. It can be seen with a amateur's telescope in very dark sky. You can see that what's happening with the moon here. They were able to know the position, because in optical it was very easy to see where the source stands, but how to identify the radio source to make sure that it is the same source that emits this blue light and the radio waves. Then I will go back just to show you the method of occultation by the moon. We knew the moon will occult this sourse, and since we know when the position of the moon, we know exactly when the object disappears, and maybe around 1 hour later or so, we see again the source reappearing in optical, and we could make it coincident with the time and the location. And by knowing the time where the radio wave appear again, then it was easy to find the location because of this occultation by the moon. And Martin Schmidt, which is an astronomer, will be 92 at the end of this year. He was able to understand the spectrum that was taken from the source, which looked very strange, like the one for 3C48, sorry. And he understood that they were the lines of hydrogen, but very much redshifted, much more than what people were able to imagine at that time, because it's a very far source in the universe. Looks like a star, bright like a star, but billions of light year away, about 2.2 billion light year away. Redshift is 0.158. And that was the beginning of a big controversy. But how is it possible that something can be so bright? Because if it is very far, to be able to detect it like that on Earth, it should be absolutely very bright. So very distant object, very bright object. So these were the two publications with the method of lunar occultation in Nature and the identification of a distance by Martin Schmidt. And also optical image that we have now, that at that time we were able to also to see again a jet in optical, the same way we see jets in radio waves, we can see jets in optical, and people were trying to remember the fact that we observed radio galaxies earlier, and now we have quasars, but we don't see galaxies. Is there a link between both of them? So what are quasars? Where does the energy of quasar comes from? Not from stars, we say, not from the nebulae. We try to answer this question. So here, it's a picture from one of the episodes of the original series of Star Trek, when they approach a quasar-like object. So this is a picture we have today. But if I tell you that it was the original Star Trek series, then it was the end of the 60s. It is a bit strange to have such a beautiful picture. It was because the Star Trek original series we remasters in 2007, but the original series in 1967, this is the way they represent the quasar-like object, because It's like a cloud, because at the time we had no way to really define a picture like what we know today. So I will not talk about the so-called AGN unified model. Again, there is someone with a mic on. Sorry, can you please mute it? I think it is Dawood Ahmad. Okay, thank you very much. So let me go back to this picture. Don't read everything. I don't want to talk too much about black holes, but let me talk about what is of immediate concern to us. What is the central engine of active galactic nuclei? What lies at the center of these active galaxies? Then there is what we call a supermassive black hole, surrounded by an accretion disk, which is represented here. And very often, this object exhibit a pair of relativistic jet, one coming this direction, and the symmetrical one coming this direction below the accretion disk. So we won't talk in detail about black holes, but we need to know that at the origin it comes from a giant star that explode, and then there is an object which is extremely dense with a mass concentrated at the center that we call a singularity. Then the rest of the black hole is made of vacuum with what we call a horizon, which is the limit we cannot approach unless we get forever trapped inside. And of course, this object doesn't radiate any light, because the liberation velocity and something trapped inside should travel faster than the speed of light to get out. And of course, it's impossible. So even the light cannot escape from the black hole. So what is very bright is not the black hole itself, but it is this phenomenon of matter falling onto the black hole. So the gas made of particle, electron, positron, light, nuclei. So they are falling, and they are disrupted also with accretion disk of matter as a tide effect. So because it's a very dense object, so there are shocks between all these particles. So because of this strong gravitational pull, then matter becomes very hot while falling onto the supermassive black hole and radiate a lot of light. And when there is a magnetic field and a rotating black hole, then some of this particle can be collimated through the relativistic jet of plasma particles. So electron, positron, and protons sometimes are accelerated at relativistic speed. So this is what we will continue to see in detail. And if you are observing through the direction of a jet, if the AGN you observe as a jet align with the direction of the Earth, then it is what we call a blazar. But if you observe it with some angle, we just call it a quasar. If it is a close by active galactic nuclei with less power, then we call it a Cepheid galaxy. When you observe throughout the accretion disk, so this is not the whole galaxy, but just the center, and there is this accretion disk of plasma and also a torus of dust around. So if you observe throughout the direction of the accretion disk and the dust, it is what we call a radio galaxy, but usually also correspond to the direction of a plane of a galaxy. So you can see that this an AGN is a generic name for all type all these classes of objects. They have a different name for two reasons. The first is because you observe a different viewing angle. And the second reason is also because it may be more or less massive black hole with more or less accretions of matter around. So then these are these two reasons: morphological difference and viewing angle. So this is another picture. I was hesitant to show you this because it has a lot of information, but mainly I wanted just to illustrate the fact that if you start around the supermassive black hole, then you have accretion disk, which is very thin. But you can see you are very small scales in terms of size. So you see that the black hole itself and the immediate surrounding of a black hole is just the size of a solar system. Then you get to something which can be maybe 100 times bigger, but then it remains still 100 times smaller. When you get the whole picture, it still remains 100 times smaller than the size of a galaxy. And this is more than the central engine here. You see this central engine with the accretion disk below. It represents a small portion of this area where you have beyond the accretion disk this torus of material here, of what we call dust, means more molecular heavy element here surrounding the massive black hole, and also what we call the broad run regions and the narrow run regions. So that's quite interesting because these are clouds that emit a light that we detect on the Earth at specific wavelengths, and they are emission lines. So that's very interesting to characterize these objects through the optical spectrum that we get from these objects. So here it's just animation to show you more in 3 dimensions what are these objects. The quasars and becoming blazars, if you are aligned with the direction of a jet, you can see that sometimes there is material ejected here, and it's why it becomes brighter at times for a few hours or for a few days. And where this material is coming from, then we think that sometimes a star can be trapped into the gravitational pull of a black hole and then being derusted by tide effect, and then it becomes more material, more accretion, and matter falling onto the massive black hole, becoming then a flaring source. So here are various AGNs, optical spectra. You can see that there are different objects. I won't go into details, but I would like to draw your attention that usually it's bright in the blue. This is the flux, the intensity you detect as a function of a wavelength given in Armstrong. So here you are in the blue, here you are in the red, and you can see that it's usually bright in the blue, the quasar, and you have emission lines which are quite broad. So if you can identify the chemical element and you will know the redshift, you will know the distance of the source, and then you can also know what are the different components you detect, a lot of hydrogen, magnesium, and so on. Then I would like to talk more about this jet. And what is quite interesting, in fact, there are many interesting things on this slide. The fact is that I told you that the plasma is relativistic, means particles are moving at speeds which are close to the speed of light. There is a beaming effect. If you are close to the jet orientation, the jet direction, then what is emitted in this way, like a sphere, like imagine a particle moving from the center to the edge of this sphere of plasma, of heated gas, then it becomes beamed towards the direction to which it travels. This is what we call the Doppler factor that we express as a function of a viewing angle, and the Lorentz factor, which is what we know well in theory of special relativity, which is always bigger than 1. And through this, we can express time dilation and distance also compression. So the Doppler factor is the boosting due to relativistic effect, and it allows us to measure the fact that the light is appearing even brighter than what it is really in reality, and why also this object appears so bright. So this relativistic beaming, as we saw with the Doppler effect also, it generates a change in luminosity, in change of frequency, and even the time interval through which the radiation is emitted. So that's an important result of special relativity. Then one thing which is very interesting to us is to be able to observe and to try to understand this light that we observe throughout the electromagnetic spectrum, and even more specifically at high energy. We want to know the mechanisms behind the production of these photons. And here you can see what we call a broadband Lcd modeling. In fact, it is a modeling of SED. What is SED? It means spectral energy distribution. Sorry, I should not have clicked here. Okay, the spectral energy distribution. So it's a measurement of the intensity emitted by your source. I mean, the flux that we receive from Earth, I should say, as a function of a frequency. So here you see you are in radio waves, then you have the optical, then you have X-ray. Here it seems we don't have much measurement. And then we have gamma rays. And we model very well from radio, optical, and sometimes X-ray. We model this radiation with synchrotron effect. Represented here, you see an electron moving inside a trap, inside the magnetic field. And there's a strong magnetic field surrounding the black hole. And through this process, this pairing electron is emitting photon. This, what we call synchrotron radiation. These are synchrotron photon emitted because of the energy loss of the electron trapped inside the magnetic field. So, but at high energy, we are not completely sure. We often model these sources with external compton, or what we call synchrotron self-compton. Means this photon and electron are able again to interact at high energy, so that electron will communicate energy to the photons generated here through the synchrotron radiation, or photons from external compton coming from, I talk about the Broadband region, the clouds surrounding also this central engine here, or photons coming from the disk. Then they can also be accelerated. Energy can be communicated by the electrons to be scattered off higher energy and account for this high energy radiation. So this is one of the possibilities, but here you can see in the jet, you see not only electrons, but you also see protons. So sometimes protons can be at the origin of high energy radiation by interacting by various shocks between plasma particles inside the jets. So now I think I should accelerate a bit. Time is running very fast. So I think I won't talk much into this detail. I just wanted to highlight the fact that if the jet is directed towards Earth because of the Doppler boosting, it appears even much brighter. This is a result of a first immediate surrounding of black hole, which was observed in radio waves in 2019 with M87 star in the central part of Galaxy 87. So for the first time, the immediate surrounding of a black hole was observed. So that was a very important result to mention. Then I will try to go back to what I said, what is a quasar and where the energy is coming from. I will try to summarize. Wikipedia says it very well. What is a quasar? It's a compact region in the center of a massive galaxy surrounding a central supermassive black hole. So this is a compact region where energy is given by the central engine, which is this accreting disk around the supermassive black hole at the center of massive galaxies. Where the energy is coming from, then I started to talk about this thermal emission produced by the heated plasma in the huge gravitational pull of a black hole at the center. Then this jet of plasma are collimated relativistic plasma jet. These jets are due to spinning black hole in a strong magnetic field. So it's why particles can be confined within this jet, very well collimated. And inside there are plasma shock waves within the jet. So I won't go into more detail. I will try to just talk about how we study this object and show you a few telescopes. So now we can rest a bit because I will mainly show you nice picture. Here is the Fermi Gamma Ray Space Telescope. Its main instrument, the Large Area Telescope, able to detect photons between a few MeV to several hundreds of GeV in space since 2008. So now we have more than 13 years of data, able to see 20% of the sky at every instant, a collaboration between several countries led by NASA. And here you can see the way the telescope is operating. You see it is observing the sky every 3 hours almost. Yeah, every 3 hours you can see almost the whole sky. So it means you have a large amount of data every day for all the sources you are interested in the sky. So we see the sky map, the same way we saw sky map in the beginning of the talk. You see here the gamma ray light, very intense, coming from the central part of the galaxy. So it's a map. It means that what is on the left corresponds to what is on the right. It's like showing a three-dimensional map all around us. And you can see some spots here of point sources and diffuse sources distributed all around. Most of them are blazars. So blazars are active galactic nuclei observed through the direction of a jet of plasma, and they constitute more than half of all the thousands of sources detected with the Fermi-LAT telescopes. You can see also a large part of unknown sources. We expect a lot of them to be also blazars, and you have a few non-blazars active galaxies, pulsars, and also a few other sources. Now about optical telescopes. In fact, in South Africa, there are optical telescopes, but also here a radio telescope, ARTREO, MeerKAT, but at SAO, there are a lot of optical telescopes, also with collaboration with other countries, also like Russia. Then here is the SARL telescope. Saida mentioned that I am also part of this, working also on data from this telescope, which is 10-meter diameter mirror. It's a mosaic of small mirror. This telescope operates on alt azimuthal mount. In fact, it's only azimuthal rotating, so it cannot observe the whole sky, because when you start observing, you don't rotate anymore when you fix the telescope at the right position in azimuth, and then it's by moving the secondary optic And here are all the instruments also, spectrograph and cameras that are able to move through this trail to observe the source. So this, even though there is a restriction, then it has the advantage to have a large mirror for a cost which was not so much compared to the big telescope in Chile from ISO or Keck in Hawaii and so on. What's specifically interesting to me is also the fact that we don't do only spectroscopy, but we can do also spectral polarimetry. So we are able also to observe a polarization of light as a function of wavelengths. So I will talk about current challenges and give a few results. I think I don't know how much time I have. I think I will try to be fast, maybe to skip a few slides. So here is an example of what we do when we model blazars. So here is a well-known blazar, which is called Markarian 421. On the left, you can see leptonic modeling, and on the right, hadronic modeling. So what does it mean? So it means for the second bump, corresponding to gamma rays detected with Fermi-LAT and with, not sure if it is MAGIC or HESS, then at even higher energy than what we can see with Fermi-LAT. So the challenge, I tell you, is to know if the gamma ray radiation produced within the jet should account from the interaction of electron, positron with the gas, clouds, and so on, or if it is coming from heavier particles like protons. So we can see that both ways are possible. We can model with electron and we can model with proton. Sometimes we can use only proton, sometimes we can use only electron to do the modeling. But for this source, it's quite challenging, but both models are working. Of course, we could argue, like Ptolemy used many epicycles to try to constrain his model, saying that it was the sun moving around the Earth. We could say we have so many free parameters that we can put, we can always find a modeling because we have different type of interaction between different type of particles. So it's why it is important to try to have a new instrument, and you have more data in gaps where you see that no data are detected. So it is one of the current challenges. We do multi-wavelength modeling, but can we always use all instruments at the same time to, if it is a flaring event, then we have to, within a period of several days, we have to trigger all the instruments which are available. But if it is a quiescent state, then it's okay. We can use data accumulated for many years. But when there is a flare, then we should have simultaneous observation, or at least as simultaneous as we can do. And we have a lot of instruments working in X-ray. You can see here hard X-ray. But the problem is that sometimes they are not sensitive enough, and some also wavelengths are not covered by any instruments. So there is something interesting also. It's about polarization measurement. When we try to understand what power blazar jet, what I have not told you before is that the thermal radiation that is produced from the disk is unpolarized. But what is in the jet, if it is synchrotron radiation, it is polarized. So that it's an interesting constraint. And we hope to do the same at high energy, but we don't have very sensitive detectors now at high energy to be able to make the difference between the proton synchrotron that will be polarized and the external quantum or synchrotron safe quantum, which is unpolarized light. So if you are able to measure the light polarization, then you can have more information about the process at the origin of the creation of radiation. So I would like to also talk about the variability, which is something important. So you can see you can open the shutter and whatever is by hand or just electric motor, then you understand that if it takes a lot of time to be opened, it can be a big window. But if it is a small window, you know that it will be very fast to open completely the window. But it is the same when you try to know what is the size of the emission region, then definitively, if it is a small region with a small radius, like this plasma blob here, and if the variability is very fast, then you know that definitively there is a small region by just trying to observe the time the radiation will be spread to arrive. But if it is a huge region, then the variability, it will take a lot of time, maybe several weeks before you are able to get the maximum of radiation, and then several weeks to get back to the quiescent state of your source. So I just wanted to present some light curve to measure this variability. It's a work I have done with some collaborators a few years ago on the 3C454.3 Blazer, the one we saw in the beginning of the Fermi sky map. And here are the variabilities that are shown. So you see, I think it's a 6-hour beaming or 12-hour. I don't remember. I think it is 6-hour here. So you see within a few hours, you can see within a few days, a very dramatic change in the brightness of the source, sometimes a very sharp peak associated. This is the time, the y in the x-axis, and here it's the flux. The bottom panel, just trying to see what are the energies. So, and we could observe high energy photons. And through we're able to find a way by estimating the wave interaction between photons at different energy. We're able to calculate the Doppler factor, and by knowing the variability time through some appropriate hypothesis, we were able to estimate the size of this plasma blob, and also able to deduce the distance of this plasma blob from the central supermassive black hole, and try to constrain it to be slightly outside the so-called broadband region, because if it is much inside, then we do expect the gamma ray radiation to be absorbed by the gas here. So I won't give details because I don't have time, but I just wanted to also talk a bit about this work we just got accepted a few days ago for publication in the Astrophysical Journal on the Blazer 4C plus 01.02, which is quite far. The redshift is 2.1. So it is a bright source, which was modeled already previously, but what was new in our study is that we were able also to do spectral polarimetry. So you can see two spectra here. They are normalized at 1, even though 1 in red is when the blazer is not bright, and in black is when the source was flaring. So when the source is flaring, we don't see much the lines, but when the source is in quiescent state, then we don't have too much background light behind, and the different emission lines are more visible. Silicium, carbon, helium. These are some of the lines we can see on the quasar spectrum. And what's interesting is that the percentage of light which is polarized is around 10% when the source is flaring. and close to zero when the source is not flaring. And this is a hint that there is a lot of synchrotron radiation in the optical. And it is also possible to give some limit of the degree of order of a magnetic field, because synchrotron radiation is produced because there is electron inside the magnetic field, so that it leads also to a constraint of the magnetic field. It is well ordered or not. So this is a result that we got with modeling made by my collaborator, Esther Schutte. She was able to model the data here in the optical. You can see radio, but radio are not modeled, but we use infrared data, so when the source is quiescent. And some of the observation we got in the optical with also LCO observatory. And here you can see these are the LCO. This is a zoom on this tiny part here and tiny part here in optical. So we didn't use the spectrum you have seen before because we could not properly normalize it. But we see data taken in 3 bands in the optical with LCO when the source was bright and when it was quiescent. And here, this is the polarization around 10%, and here close to 1 or 0. And the modeling of this source at different wavelengths, giving the constraint of the level of polarization as a function of wavelengths, allow us to estimate the mass of a supermassive black hole. And we found that it was 3 billions of times the mass of the sun. It was also previously estimated, and it could be, we try to compare the estimation that can be obtained also by using only the emission line without considering the spectral polarimetry. And it leads to some compatible results almost.
Michel?
Oui? I am too late. Sorry?
I think we could wrap up now because we.
Okay, yeah. Okay, I will skip this just to see that we were able to estimate the distance of a source which was flaring. So I will skip that, and I will try to go to the summary and the perspective. Sorry, the computer is a bit too slow because there are too many slides. Okay, so I will just give this summary. So I want to say that optical and gamma ray monitoring of blazars and other AGNs offer great potential for astrophysical modeling. We have seen that we can estimate the size and location of gamma ray emitting regions, the distances through the observation with spectrographs. We can estimate the mass of the supermassive black hole. We can estimate the AGN type also. And we can try to understand what are the radiation mechanisms involved, the strength of magnetic field, etc. And for those who are interested in this field and want to study, you don't need to be a member of any publication because the data from Fermi-LAT are freely available online. And many many archival data are found at various wavelengths, also publicly available from the web. Also, we expect soon to have gamma ray data at higher energy than what we observe with Fermi-LAT. We have instruments like HESS, Veritas, MAGIC, but we are not allowed to use their publication if we are not collaboration member, but with the Cherenkov telescope array, then there will be more sensitive data and freely available to all. Optical data also with LSST. We will be able to also have X-ray polarization data through the Koenig experiment and even in gamma ray with AMEGO. So this is CTA. I won't talk about it much. It will be a large array of Cherenkov telescope located at 2 different locations, one in the northern, one in the southern hemisphere. EXP, X-ray polarimeter, so being able to detect polarization at high energy. It's possible now, but we don't have an instrument sensitive enough to really give strong constraint on AGNs. And Amigo, it's quite interesting. So it's just it will be an international project. Just on the paper, it's not built yet, but it is to be able to see what lies between hard X-ray and soft gamma rays, where we don't have any detector now working. We had Comtel, but it was previous century. But now we have Fermi-LAT, but we don't have energy to have a bridge between X-rays and gamma rays. And also you can use also archival data from the Steward Observatory and even polarization data and spectral polarimetry. And I told you about the Fermi data that you can publicly access. And here is my conclusion. If you are interested in the fields of active galactic nuclei, then you can study them through different wavelengths, gamma rays, radio, optical, and so on, measure their redshift, study the time variability, the time pattern, and model the spectral energy distributions. Thank you for your attention, and sorry, I'm often too long, so it's difficult to make the right choice of what to say, what not to say, because there are so many things to say. And I think it remains still just an introduction. So thank you.
Thank you so much, Manisha. That was very interesting. I think we have a first question. I don't know if you can see it.
Yes, I see it. So the question is, what kind of spectrum does an AGN produce? Is it it's a continuous spectrum and a line spectrum. Well, that's a good question. I think I should have mentioned this, but let me go back to one slide where we see some spectrum. There is a continuous radiation produced by synchrotron, and here, can you see that? So let's take the spectrum of a mean quasar, which is the same as the blazar, just the orientation is not the same. So you see the continuum, which, depending on the source, if it is a blazar, then, and if it is flaring, what will dominate will be the synchrotron radiation from the jet. But if the quasar is not flaring, then it will be more of the thermal radiation, the continuous thermal radiation, the black body radiation, in fact, coming from the accretion disk. And the lines are coming from the broad run region or the narrow run region, if they are narrow. So it means it's also thermal radiation, but coming from the interaction of radiation with a specific chemical element. The same way people do in laboratory when they do solid state physics also to identify chemical elements in some samples.
Okay, thank you. Do we have any other questions? No?
Okay. Students, you want to ask something?
Hi, thank you for a nice talk. I have a couple of questions. One is the AGN spectra that you showed, or the variability that was evident there. Do you know what is the source of this variability, and is it periodic or non-periodic?
A good question. Periodicity for this type of source has been found maybe for one of two sources. It could be, if it is like two black holes, it would be the same type, because it has been observed periodicity for X-ray binaries, but usually it's not periodic. There is no periodicity. It means we cannot expect when it can happen. So we should always check. So every day I check the Fermi-LAT Frère Advocate emails, because they will tell us, okay, the source is flaring in gamma ray. Let's try to observe with multi-wavelengths. So this variability, we expect that there is some amount of material which is added to the accretion disk. Could be like a tidal disruption of a star falling into a gravitational pool of a supermassive black hole. Or it could be, I don't know, maybe some nearby supernova that create a shock wave. So there is, for some way, more material is falling into the supermassive black hole. And I think probably it can be interesting to see again this animation where we see material here being falling into, we don't see material falling into a black hole slightly, but we see maybe some brightening at the center, and sometimes there is something ejected through the jet. And this light curve is from a blazar, so it means we observe very close to the direction of the jet. So it's where we see the material. So some people say, I never try the experiment, that if you have a top, the toy for the kid, and then it is rotating, and if you throw water on it, then it will be collimated as a jet towards a specific direction. So maybe we should try to see that. It's the same thing. I don't know, do I answer your question?
Yeah. Okay.
And then there is another one in the chat window. Okay, what can be the source of Lyman alpha forest in the high relative quasar spectrum? Does I think Lyman alpha forest provide issue with observation and interference in the spectrum? That's a good question. I not specialized with this, but yeah, like for ordinary galaxies, I think when there is clouds lying throughout the line of sight, well, how it can be rectified, I'm not sure. I mean, if we get enough lines that are compatible with the same redshift, I think it should not be a problem. But of course, the Lyman forest maybe could be there, and suddenly we might have some one redshift coming from the Lyman forest, one redshift coming from the source itself. We could be confused, but I think that when we get several lines, then the confusion should not be there. I never heard about this issue, so I'm sorry I cannot answer in more detail.
Do we have any other questions?
The one I didn't show you because I didn't have time is that initially we got a spectrum with only one line. So we say, okay, it looks like NG2 line, but finally we got another spectrum with another line, and we confirm the redshift. So yeah, it sometimes can be challenging depending on the type of source. Yeah.
I'll ask you one question, Risha. Can you list one or two of the biggest mysteries we have about AGNs?
Interesting question. Let me go back to my conclusion slides, maybe the summary slide. What is the source? What are the different mechanisms at high energy? Get back, I have a lot of background slides. Yes. There are many, so I think I may forget some of them, but definitively the radiation mechanism involves mainly at high energy. And I was thinking of something. Also, how they form initially. Blazars and quasars are seen at very high redshift, but radio galaxy and Cepheid galaxies are AGNs, but with low accreting power, and they are close by. But quasars, with the Hubble Space Telescope, we could see that they were also the center of galaxies and not only a blue spot in the sky for many of them. But still, the challenge is to try to understand how they form. And if they are still very far in the universe, it means that the universe was young when these quasars were formed. And still, we would like to understand more how the supermassive black hole can be formed so early in the history of the universe. Because for a black hole to grow, it should have got enough time to eat a lot of material. So that's also one of the interesting challenges. But there are many more. I should have made a list. And the understanding of radiation, yes.
Okay, so thank you so much. For me, I found this interesting. And thank you for taking the time to talk with us and explain about AGNs. And Alain?
Thank you, and please don't hesitate. If you have other questions, you can still email me. I can also send you the slides.